So good morning, everyone. We wait a couple of minutes because I can see participants are still joining. I would say we start in 2 minutes or when the number of participants seems to have stabilized. So bear with us. So, good morning, everyone from Copenhagen, and a warm welcome to all of you behind your screens to this Copernicus Land Monitoring Service webinar. I'm Manuel Mayr, and I'm responsible for the implementation of the current production of HRL Imperviousness on the side of the European Environment Agency. And today's webinar is all about Copernicus. I believe it's fair to say standard product for soil sealing across Europe, the high resolution layer imperviousness. And we will cover today how it's produced, what you can expect from the data sets, how you can access these layers and products, and also how this data is currently being used and how you could maybe use it. But next slide, please. First of all, some housekeeping. This webinar will be recorded and made available afterwards via YouTube. I believe your cameras and microphones are switched off by default. If you have been following our previous CLMS webinars, you're well aware that we like to use Slido. First of all, for you to post your questions throughout the entire webinar. And second, to collect your opinion on a small number of questions that we have prepared. So feel free to scan the QR code at the bottom right of this slide already now and enter the numbers directly into the Slido app to be prepared when it's time, and we will let you know. Next slide, please. Right, what have we planned for you today? I will briefly provide some background. We will then take a look at the upcoming Imperviousness 21 production and receive first-hand information from the implementing industry consortium. We have Stefan Ralser from GeoVille, who is responsible for the technical implementation, and Stefan especially for the data processing. We will then receive an overview by Eva Poglitsch, the project coordinator on GeoVille site. And we also cover the resources that we have available for you besides the data. And then we switch to the applications and use cases of imperviousness. Again, I will provide a quick overview. And we will then have, and I'm very happy that we have him with us today. We will then have Christos Mamidis from the Jiushangbana Tropical Botanical Garden. He's an associate professor there, and he will present his recent study where they used imperviousness in the context of conservation. And afterwards, we have Katja Kostura from GeoVille as well, with a live demo of a Jupyter notebook to support urban climate assessments with the help of imperviousness. And after that, it's, of course, time for your questions, and we will do our best to answer them. before I will quickly summarize and close with an outlook on the upcoming releases. Next slide, please. So let's try Slido for an initial questions and to get to know today's audience a bit. So how would you rate your prior knowledge of HRL imperviousness and the contained layers? It could be that you're not at all familiar with the dataset, or that you are an expert user that uses it since several releases. Just let us know. We will give you some time also and we can monitor, of course, the participation here, which I unfortunately don't see as it seems, but I'm sure our colleagues in the back have this covered. Next slide, please. Yeah, artificially sealed surfaces are created usually through the replacement of original natural or semi-natural land cover, and these are often replaced with impervious materials, most prominently asphalt and concrete. And this sealing has widespread implications for microclimates, almost any soil function, I would say, such as water infiltration, obviously, productivity, but also soil biodiversity. But also, if we look at it in a broader spatial context on the connectivity of landscapes and contained habitats. It adds up that soil sealing is typically long-lasting and largely irreversible, or at least very tedious to reverse. And as land is a limited resource, mapping soil sealing as a phenomenon in space and time captures the processes and dynamics that result from the ever-progressing urbanization and economic development, but also reflect our ambitions for a transition towards more sustainable use of land and also preparedness for the outcomes of climate change. And I would say this is a strength of this imperviousness products, that the definition considers sealing from a land cover perspective, and it is independent from varying national definitions that could also be based on land use and may include also non-sealed areas. So it is an independent reference that ensures comparability of the phenomenon and the processes behind across Europe. To give you some background, imperviousness nowadays covers an extensive time series, as you can see from the right, that will soon be extended by products for the reference year 21 and also 24. And it all started with a comprehensive and very ambitious mapping back then of a so-called degree of soil sealing for the 2006 reference year. And until the reference year 2015, imperviousness was mapped at 20 meters. From 2018 onwards, we then switched to a 10-meter resolution, making full use of the Copernicus Sentinel-2 time series. And we also introduced a new subclass of imperviousness, the so-called Impervious Built-up. And with that, I think we are ready for further details on the current production, and I would like to hand over to Stefan.
Yeah, thanks for the introduction. So I will present to you some aspects of the technical implementation of the imperviousness products. I will focus here on the status maps, status map production, both for the built-up component and for the imperviousness density. I will start on the next slide with with a brief overview of what the product actually is, and give you some key technical specs. So as said, I will focus on the primary products, which are the status products for imperviousness density and imperviousness built-up. But the portfolio consists actually of a lot of different layers that are delivered along. Most notably the change layers, so giving you information on which areas have changed from the previous production to the current production. And both layers are also supported by auxiliary layers, which give additional information on the status and the change layers. So I will focus on the production of the newest product, which is the 21 release of the product suite. So this will be released very soon. The first product was available in 2006. In a 3-year update cycle, we've come now to 21 that will be released soon. And we are currently also working on the 24 products. So the area covered is EA 38 plus UK and the French DOMs. So the next slide, you can see an overview of the product properties. So this is a raster product in a 10 meter, 20 meter, or 100 meter resolution, depending on the product type. And it's delivered mostly in European layer projection for the most part, except for the French DOMs, which are in local UTM projection. And the target accuracy is 90% for both the user and the producer accuracy. Yeah, in the next slide, you can see here an overview of all the products that are contained. As said, there are primary layers giving you status information on the imperviousness areas and on the built-up areas. There's a third one, the so-called share of built-up layer. This is a downsampled version of the imperviousness built-up. In the middle, you can see 2 examples of the change layers for both, again, the built-up component and the imperviousness component. They are mostly in 20 meter resolution. And on the right-hand side, you can see an example of an auxiliary layer. In this case, it's the confidence layer for the imperviousness density. But there is also similar information available for the built-up component, of course, and also for the change layers. Yes, on the next slide. Yeah, actually, so what we are implementing here with this 21 update was a fully automated process. So in the example, you can see an RGB image. This is the airport of Innsbruck. And we want to have a fully automated process that can go from this type of information, so satellite data, of course, this is just an example, to a fully automated mapping of imperviousness or built-up areas. So now you can imagine that, so we are using Sentinel-2 data across 1 year. So this is a lot of data. We are using every single scene, and of course, these are also there's also cloud cover, and there's some challenges that need to be solved. So this requires a sophisticated pre-processing step. And in this pre-processing step, we are reducing this huge amount of data from 1 year of satellite observations to actually a well-defined set of input layers that are used in the machine learning process in the production. And here we are always focusing on 3 different types of data extraction. So we call it the 3 pillars of information extraction. That's on the one side, it's the spectral domain. So there we are asking which color does a single pixel have, so to say. This is a static information and already contains a lot of important information for the mapping. But also, as said, it's static, and another type of information that need to be accessed is the temporal information. So how does a single pixel behave over time? For example, how does it look like in winter? How does it look like in summer? This is a different type of information. And the third type of information that we are accessing is the spatial neighborhood, also very important. So we are looking at not only at the single pixel, but at the whole spatial neighborhood, at the structure that is surrounding a single pixel, which, for example, is very important to distinguish between actually a building and a flat sealed surface, a parking lot, for example. And the next slide. Yeah, you can see here, I've put together 2 examples coming from the spectral domain and the temporal domain. It's often easier to look at images. What I want to show here is that on the left-hand side, you can see a RGB composite. This is something where we as humans are very used to look at. This looks kind of natural. On the other hand, on the right-hand side, this is a false color composite coming from the temporal analysis. And what I want to show here is that these two images, they look very, very different. And this is a good thing because this means that they contain a different type of information. And our machine learning models, they are able to use these layers in a combined form. So again, the example is we as a human, we can only detect, so to say, 3 channels at the same time, red, green, and blue. The machine learning models, they can use any number of input layers. And for the production here, we are actually using 11 layers coming from the spectral analysis and 7 layers coming from the temporal analysis. Now there is a third type of information extraction that I mentioned. On the next slide, you can see the model that we are using. So this spatial information extraction, so the analysis of the structure of an image or of the surroundings of a pixel. This is incorporated in the special type of machine learning model. We are using here a convolutional neural network, so-called UNet. This is now also widely used in many remote sensing applications, actually. And this UNet model can learn to, so it takes as an input the data from the spectral and temporal domain and can learn the spatial neighborhood. So this takes not only a single pixel, but it uses patches of images to map, to predict the desired output. Now, how is this done? We need a training process to create these models. And in this training process, we are giving the model examples of imperviousness data and of built-up data. And the model can then learn to extract this information from the input pre-processed satellite images. The training data is shown on the next slide. There is, of course, we need to train 2 different models, one for the built-up component, one for the imperviousness component. And for both, we have very good ground truth data available. For the built-up component, we're extracting this ground truth information from vector building footprints. They are coming mostly from OpenStreetMap, but also Microsoft and Google offers freely available building footprints. And this gets rasterized and incorporated into the training process. Also for the density, we are, for the imperviousness density, we are in a lucky position because there we can use the previous production, in this case from 2018, as the main training source. There's a small detail. We have complemented the training here also with data coming from the CLC Plus backbone product. But in general, it is, in this case, it's trained in 2018. Then the models learn to predict this data and can be applied to unseen situations. So in this case, the model is trained in 2018 and then applied to new inputs from 21 satellite data. The next slide. I want to show you some examples on how it looks like. So these are the 2 main status products. On the left-hand side, the imperviousness density. On the right-hand side, the built-up. Now, the main difference here, what you can already see at this scale, is that the built-up component doesn't contain the streets or also the airport runways in the north, for example. They are not contained in the built-up, but of course they are contained in the imperviousness product. On the next slide, you can see an example of, so this is an animation going from 2015 to 18 and 21. And here you can see two things. The first thing on the left-hand side is that you can already see at this scale that the quality has improved quite a bit. So from 2015 to 18 and 21, much more details were added to the products. And on the right-hand side, you can actually see real changes that have happened between 18 and 21. And yeah, they are contained in the change products. In this case, it's a classified change that I'm showing. And on the last example, I want to show on the next slide. So this is a collection of all the layers that are delivered along with the production. As I said, there's the main products are the status products, and yeah, there are several products outlining the change, and also auxiliary layers for the confidence, for example, and for the support of the change layers. So with this, I'm at the end of my part. I want to hand over then to my colleague Eva. She will present the data access part of this presentation. So thank you.
Thank you very much, Stefan. Yes, so now that we all know what the imperviousness portfolio is all about, I will briefly guide you on how and where to access the data. So please, let's move to the next part. Yes, so basically we have three ways how to do so. We have the EEA CLMS portal, we have Vekeo, and then we have the GeoServer. All three platforms basically provide you with access to the data, but they somehow serve different purposes and also offer different functionalities. And that's why I will briefly describe each of them. Please, let's go to the next slide. So the first one is the EEA CLMS portal. This is very straightforward, as you can access the products directly from the official CLMS website. Yeah, so it's basically a map-based viewer that allows easy data browsing, visualization, and download, but only of the CLMS products. Yeah, it's basically meant for a quick exploration of the product, and it's definitely meant also for less technical users. Let's go to the next one, please. So the second option would be the harmonized data access hosted on Vekeo. So this is meant not only for accessing and downloading the data, but also for processing the EO data directly in the Vekeo cloud environment. Also, it's API-based platform, and also here the users can select their dedicated area of interest. And also it actually gives opportunity to the users to play around a little bit more with the data, as you can combine, for example, the imperviousness data also with any other Copernicus data sets, also apart from the land monitoring only. Let's go to the next one. One more thing, actually, I'm sorry, I forgot. I wanted to mention regarding the Vekeo that, and this is actually very important, especially for the 2021 update that will be released soon, as Stefan mentioned. On Vekeo, you can access actually all layers that are part of the portfolio, so including also the auxiliary layers, such as the confidence layers and the change support layers. And here now we are at the GeoServer. That is the last option how you can access the imperviousness data. GeoServer offers seamless visualization of the product through the hosted cloud optimized geotiffs. Those layers can be then very easily embedded into any web application using the WMS. Let's go please to the next slide. Yeah, the last information that I would like to share here, that apart from the product itself, also relevant documentation is provided for users. And I would like to particularly highlight two documents. Those are the product user manual and the algorithm technical theoretical basis document. Both are accessible via the CLMS portal. Yeah, that's it from me. Thank you very much. And I will hand over back to Manuel.
Thank you, Eva and Stefan. Yeah, we now move to a different topic, actually. That is really how data can be used, how data is used. And I will again start with an overview. So next slide, please. Yes. So there are numerous known areas of application of imperviousness, and I would only like to mention a few here. So I would say the first really is, imperviousness is used for official European soil monitoring and the creation of so-called statistical indicators that are based on our imperviousness time series here. And they are created by our thematic colleagues at the European Environment Agency. And as you can see to the right, for example, they give sealed surface increments over time for countries, but also, I would say further advanced indicators or measures such as the sealing area per capita, which of course is a kind of proxy for land use efficiency. And you can often see the other way around, that often rural areas, for example, have higher per capita use of sealing. Apart from that, there is also indicators more targeting the ecological outcomes and the outcomes on landscapes and the habitats from sealing, so-called land fragmentation. Of course, it is probably straightforward that imperviousness facilitates monitoring urban sprawl, and also the usage for urban and regional planning purposes is a well-known use case here. Also to characterize local and urban climates as a baseline for climate change studies, imperviousness has been proven very useful at different levels or different spatial levels. For example, you see like a national level here in a study from Germany. There's also European local climate zones derived with help of imperviousness and other Copernicus Land Monitoring Service products, but also on the local level, imperviousness has been used. And in general, I would say imperviousness is also a set of baseline products that can be useful inputs to different downstream products and modeling activities generally. If we consider, for example, simulation in an urban environment for flooding scenarios, or the efficiency of climate change or climate adaptation measures. And I believe there are many more, and I would also like to point you to our CLMS use case section. I've included the link above, where we highlight some of them and where you can also contribute with your use case. Next slide, please. Before we move to Christos and his study, we would like to know from you which application actually best describes your intended use case. And we have also defined some options there, but of course you can enter your usage or your intended usage of the data set directly in Slido. And as we have new participants also joining during the webinar, I would like to once again highlight that you can use, and you should use, in my opinion, also use Slido. You can use the QR code or enter the code there on the right of this slide. Okay, with that, I would say we go to the next slide, and that is also now on Christos.
Thank you, Manuel. I will share how we used some of the layers mentioned earlier to study habitat loss due to the expansion of impervious surfaces. So for this particular project, we had two specific objectives. The first one, obviously, to quantify impervious surfaces across the habitats, across different habitats in the EU in an effort to understand which types of habitats might be most vulnerable to these surfaces. And the second objective was to understand to what extent Natura 2000 sites can limit the expansion of these surfaces and protect European habitats. And for those not fully familiar with Natura 2000 sites, these are essentially protected areas across the whole of European Union. We have more than 27,000 such sites currently, and they cover approximately 18% of the EU's land area. Next slide, please. So before I present some of the key findings, let me give you an overview of the datasets and the methods we used so that you have a clear idea of what we did exactly. Starting with the datasets, of course, we use the layer that quantifies the density of impervious surfaces across the EU at a resolution of 100 meters. Given that we were also interested in quantifying change and potential increase, we also used the two change layers that were available back then for two different time periods. We used the ecosystem type map, also available by the European Environment Agency, and I will give you a few more details shortly about this map, just so that you know exactly which habitats we analyzed. And lastly, we also use the Natura 2000 database, which essentially has the boundaries, the exact boundaries of all these Natura 2000 sites. Next slide, please. I won't go into too many details about these three layers, given that we have already heard about how they're produced and what they represent. So next slide. I want to spend a bit of time discussing this ecosystem type map. Essentially, it shows the distribution of the different habitat types across Europe, again at a resolution of 100 meters. And you can see on your screen that it has 10 main categories. For the purposes of our project, we excluded category A, which refers to marine habitats, as obviously those were not relevant to our objectives. And we also excluded the last category, the industrial and other artificial habitats, as those are not particularly important for biodiversity. So for this project, we ended up analyzing 8 different categories of habitats, ranging from coastal habitats to grasslands, woodlands, and forests, and so on. Next slide. Just to give you an idea of what we did exactly, in the panel on the left-hand side of the slide, we see two figures. This is an example of a Natura 2000 site. This one is found in Portugal, and figure A shows essentially the different habitats both within the Natura 2000 site and in the surrounding area, right? And the figure on the right, figure B, shows essentially the density of impervious surfaces. And going back to our two original objectives, the first one was to quantify the density levels across the different habitats to see if some habitats are more vulnerable than others, and also to compare what is happening inside the Natura 2000 sites versus outside to see if the Natura 2000 sites are helping to maintain the natural state of these habitats. And to achieve this second objective, we relied on a statistical method called matching analysis. Without going into too many technical details, essentially the advantage of this analysis, as you can see on the right, is that it allows you to match sites within protected areas to sites outside, while you control for a number of other variables that are also determining the levels of impervious surfaces, right? And slope, it's a good example of such confounding variables. We know that areas on steeper slopes tend to have lower levels of artificial surfaces, regardless of the protection status, right? So by using this technique, we were able to compare areas inside and outside and attribute those differences to the protection status. Next slide. Next slide, please. So now going into the results, looking at the overall patterns, essentially what we see, three habitat types stand out. The first one, the one with the highest percentage of impervious surfaces, is habitats associated with farmlands, right? And farmlands, especially low-intensity farmlands, can be very important for the conservation of many European species. But here we see that they have the highest level of artificial surfaces, and in a sense, it's not unexpected, given that these types of habitats are associated with higher human presence and therefore more likely to have these kind of surfaces resulting from roads, for example, and other similar areas. The second habitat that showed relatively high levels was grasslands, and we think that this is the case because grasslands, they are usually found on flat areas and they are relatively easy to convert into artificial surfaces as opposed to, example, to woodlands and forests. And lastly, the third habitat was coastal habitats. And this is because this is likely due to competition with a lot of other land uses. A lot of these coastal habitats are found in areas where we see high levels of development and increased tourism activity, right? So due to competition with these other land uses, we see these higher levels of artificial surfaces. Next slide. Going into the comparisons between Natura 2000 sites versus outside, here we see two interesting patterns. The first one is a very positive pattern, and it shows that the level of impervious surfaces are always lower within Natura 2000 sites, represented here with the green color. But we do see differences between the various member states. For example, if you look at Malta, you will notice that the levels of impervious surfaces are relatively high, both inside and outside protected areas compared to Finland, for example. Next slide, please. And this is a pattern that we actually saw for the different habitats also. Again, we see that the levels are always lower within the Natura 2000 sites, but they vary across the different habitats, right? And the three habitats that I mentioned earlier, they stand out. Just to give you an example, if we look at coastal habitats, we see that the levels are even within the protected areas, they are higher than woodlands and forests, for example, even outside protected areas. Next slide. Now, looking at the increases at the change of impervious surfaces, we see again that those three habitats, they tend to experience the highest change. And the change is actually higher during the most recent period examined compared to the 2012 and 2015. And another pattern that we see that it's interesting is that some of that change is happening also within the protected areas, right? Although again, the increase, the change is lower within the protected areas, there is still some change happening, even especially for those three habitats that I mentioned earlier. Next slide. So what do these results mean from a conservation point of view and from a policy point of view, especially in light of the EU biodiversity strategy? There are a few key messages here. The first one is that Natura 2000 sites, they seem to be effective at reducing the extent of impervious surfaces and also the rate of increase. That said, certain habitats, such as coastal habitats, they tend to be slightly more vulnerable than others. And we see that for those habitats in particular, there are still increases going on even within protected areas, right? So protected areas do not completely stop the expansion of impervious surfaces. So this means that although the Natura 2000 sites play an important role, and this is particularly important given the fact that the EU is planning on expanding this network of protected areas, The results show that we also need other tools and other policies to mitigate this impact on habitats of conservation importance, and especially habitats that will be outside the protected areas, right? So in those cases, strategies such as land recycling and strategies that aim at reducing land take can be particularly useful, especially in member states that have the highest levels of impervious surfaces. So this is all from my side. I would be happy to discuss this further if there are any questions later during the Q&A session. And I will now pass the microphone to Katia.
Thank you, Christos. Yes, I will now briefly guide you through a Jupyter notebook that uses high resolution layer imperviousness dataset to explore local climate risks in urban areas. So the main problem that we are investigating in this notebook is about heat in the cities. As we know, the temperatures are rising due to climate change, and that in combination with increased surface ceiling makes cities prone to heat retention, excess heat, which then leads to urban heat island effect, which is a higher temperature than in surrounding areas. And the goal of the notebook is to use imperviousness data in order to explore urban heat island effects in Austrian cities using interactive visualizations and computation of basic statistics. The notebook is available openly on the EEA GitHub, so let me head straight there. I will now share my screen, so if you don't see it, please let me know. But what I'm now showing is the repository of the notebook, and all of the material can be downloaded freely and run locally. But we also provide a link to a binder environment, which is this button here, which allows one to run the notebook directly in the browser, so no local setup is required. So once I click on this button, an environment starts setting up and the notebook will open. So the notebook contains introduction into the topic, as well as interactive visualizations and the computation of some basic statistics in order to analyze the interplay between imperviousness and urban heat. I will not go into the details of the notebook. I just want to show you some of the main features that can be explored. So apart from the imperviousness data sets, here we also use mean summer afternoon land surface temperature data set. And both of these data sets are shown over the entire extent of Austria at the beginning of the notebook. The user can then proceed to select a region for further analysis. So several options are available, and we can choose one. And we can then proceed to plot both of the data sets side by side, which is shown here. So these maps are fully interactive, so we can pen, zoom in and out, and the data sets move simultaneously. So this can then be used to really explore in detail the imperviousness data sets of the selected region, and moreover also to see how indeed moving from areas of low to no imperviousness toward higher imperviousness, how it affects the temperature. On the next map, we show both of the data sets overlaid on top of each other. And the layers can be toggled on and off to analyze this correlation interplay in a bit more direct way. So here, yeah, one can then really analyze, for example, how this impervious area here indeed corresponds to higher temperatures than the surrounding area. In the rest of the notebook, the user can compute some basic statistics for the region, such as mean value of the temperature and imperviousness, percentiles. Histograms can be displayed, where we show the distribution of the values for the region and the correlation between the mean surface temperature and the imperviousness. And further down the notebook, there is some additional analysis available. For example, we can choose a window of imperviousness for analysis. So here, for example, I can choose one value and then show only the pixels which have impervious degree of 40 or larger. And this is shown then on the next map. So it is the same map as above, but now limited to only a certain window of imperviousness. And also mean values are displayed. And then by choosing a different window, one can then really analyze how going to higher imperviousness windows, one gets higher and higher temperatures and more isolated, more significant urban heat islands. So yeah, this is a short overview. So as a summary, this notebook can be used as a way to analyze the interplay of imperviousness and urban heat. And in particular, it shows that imperviousness can indeed be used to provide insights into things such as thermal comfort and heat stress in the cities. As I already mentioned, the notebook is available freely on the EEA GitHub, which is with the link shown here. Or you can also scan the QR code here, which will take you directly to the notebook repository. And I encourage you to have a look and explore the notebook for yourself. Thank you. So that's it from my side. So we can now proceed with the next slides and the next section.
Thank you, Katja. Very informative, and also Christos, very nice use case. Thanks a lot for sharing. I'm sure there will be some questions. I would like to add to Katja's contribution that this is currently enabled for the upcoming 2021 dataset. And it is also, you can also execute it directly online on a platform. So there's no need for you to really work in a own cloud environment to execute it. But to continue further, we have now heard some usages and very nice examples how the data sets are used. And still, we would like to get better, and we would like to know what kind of type of additional support would be most beneficial for you to use HRL imperviousness. So which additional measures can we take? More online tutorials or dedicated workshops? Would you like to hear further, see further Jupyter notebooks? The Slido question is open for your opinions here. Please use it, please help us, and we will try to consider them. So I can see we already have a growing number of contributions. Before we move on actually to the next slide, which I have, which I know is unfortunately another Slido question, but I promise it is the last Slido question that we have for today. This is something that we would like to ask you as a kind of reflection of this webinar. How useful would you rate this webinar from 1 not being useful at all to 5 being very useful or the most useful? Please, we will leave the question open, and you can enter it anytime, but please make sure before you leave that you evaluate this webinar. Next slide, please. Yeah, we are now going to the question and answer section of this webinar. And we have already received, quite a sufficient number of questions, but I invite you to still post your questions in the Q&A in Slido. And we will continue really taking them as they appear in the popularity. And I can actually see that the first two questions are targeting the release date of this upcoming product. So the first question is: a timely publication of IMD layers is crucial for national level applications. Can this be improved in the future? My answer on this is yes. It would be a pity if we cannot improve it. We know that we have a delay here, and it was actually something that I reserved for the last slide. But I can assure you that we will soon publish 21, and 24 is, as Stefan mentioned, already in production. And the plan is that Imperviousness 24 will be published beginning of, or say in Q1 next year. So as you know, we can only start production once the image data for the reference year is available. So we start right away after that. And I think it is very timely if we can commit to a publication of 15 months after the reference year ended. The next question is, this is more a bit technical, and I would probably forward that to Stefan. So the user says, or the participant says, I find it difficult to understand how the model is able to distinguish between IBU, that is the imperviousness built-up, and the sealed surfaces, that is the IMD, by only using optical satellite data. Can you explain this? And Stefan, please.
Yeah, sure. So, of course, this is a difficult question, indeed. So with this special type of machine learning model that I showed here, this convolutional neural network, this is really the heart of the process here that can incorporate a spatial understanding, actually, of the neighborhood. And I like to imagine this as a similar process than we as a human are looking at an image. Actually, we can also distinguish it from an optical image, right? So the information is there. And also, if you think about how you as a person are looking at these satellite images, you're not looking at it very zoomed in or very zoomed out. You're doing you're zooming in, you're zooming back out. You're looking at the larger spatial context. You're looking at the very small spatial context of the colors, of course. And the model here, in a sense, does the same. So it is, if you remember this, it's called the U-net. It's a U shape that the model architecture is building. And this U shape is kind of, you can imagine it as this zoom in and zoom out process. In this U shape, it's scaled down, looking at the larger scale neighborhood. Then there is so-called bottleneck. And then after this bottleneck down there comes an upscaling again, which uses information from the downscaled versions, mixes it all together. And with the examples we are giving the model during the training process, it is in fact really able to learn this spatial, temporal, and spectral relationships in the data in order to produce the desired outputs. I hope this could somehow explain it. The details are, of course, very complicated and would require its own presentation, actually. This is kind of an overview how I understand it.
Thank you, Stefan. I would also like to point for really further details. Also, this question to be answered by the upcoming documentation. We have a product user manual for you in the box, and also an ATBD, so an algorithm theoretical basis document, where this is described in detail. And of course, if there are any questions after reading that, please come back to us anytime. I would take the next question, and this is about the change layers. So I'm afraid, Stefan, this will go to you again. So the question is, the change layers, is it the difference between the two status layers, or what is it?
That's a very good question. As said, I didn't focus on the production of the change layers. There are some details that need to be mentioned. This is all explained again in the technical documentation. For the change layers, it's a bit tricky because just doing the difference of two status layers would include a lot of what we call technical changes. These technical changes, they appear, for example, when certain parts of the status layers have been improved. So the old status layer isn't changed. The new one, for example, as it was in the 21 production, includes more details, for example, the street network. And subtracting these layers would lead to a situation that where these streets would appear as actual imperviousness changes, which is not the case. For that, we are incorporating an additional filter step in between. That's looking again, that's an independent analysis of the satellite data. And it can, so during this process, we distinguish between areas that were really affected by changes seen in the satellite data, and areas that are not actually where no change actually happened. And this is the reason why we are including these change support layers in the product portfolio. These are exactly, so the change support layer plus the change layer equals the total change. So this, in there you see the distinction of the actually product adaptations and the real changes.
Thank you, Stefan. You already answered part of the next question. That was actually, what are the support layers? But still, this question continues. What are the confidence layers? Can you say something? How do we, in easy words, derive the confidence layers? Is this an output of the algorithm, or is it some kind of accuracy assessment that we do?
Yes, sorry, there was some noise in the background. The confidence layers, they are created during the prediction process, during the application of the model. And here we're using an ensemble prediction in detail. So we are not predicting once, but we are predicting several times, actually for models that have been trained in the surrounding areas. And with this, we get information on the direct information on the prediction confidence of the model, and this is then put into the confidence layers, giving information on the quality of the prediction.
Thank you, Stefan. The next question is more to the API. So is there an API to request the data in the CLMS platform? So our very own platform and website for automated large-scale applications. And the answer here from the person who asked the question is, or the background maybe, is that Vekeo is a good idea, but we already use other clouds. I mean, currently API access is only facilitated by Vekeo, but I understand Vekeo is rather flexible also to access with different clients. And as some of you might be aware, the midterm perspective really is also to move the data from entire CLMS to the so-called CDSE, the Copernicus Data Space ecosystem. But this will still take some time. You can already find some of the products there. Unfortunately, I don't know which other clouds the question is referring to, but yeah, please get in contact if you have further needs there. And then there is another question on the Jupyter notebooks. They look very useful. Is it planned to extend the coverage to other member states as well? And maybe I can try to answer this. This is certainly now a demo use case. But if there is justified needs to extend, if you can request this also and make your needs clearer to us, there could be a possibility, I would say, to make this scripts, to extend the scripts and also maybe make them available to other areas. Having said that, I think we are already over time. And I can reassure all the questions that were asked will be answered in, or the remaining questions will be answered in a post-webinar reflection. So all participants will receive this. And as such, I would like just to go to the next slide, or the next slide. And that is a kind of summary. So we have seen that imperviousness is mapping soil sealing and change across Europe. It has a rich time series already, and it has an aligned subproduct for built-up areas, which are mainly buildings and above ground constructions on a binary basis. And for this data set, 21 will for the first time also deliver a change layer. And we have also seen from Christos and Katja that these data sets that we produce here really facilitate diverse applications and also usages in different domains. And as for the roadmap, we will, in the next couple of weeks, finally be able to publish Imperviousness 21. In case there is a justified urgent need for you to receive a subset of the data set, please get in touch with our CLMS help desk, and we will try to facilitate early access. And as I mentioned, the upcoming production 24 is underway, and the publication is currently planned for Q1 26. In addition, we also plan to validate 21 and 24 productions in an independent manner. This will take place once 24 product is produced or production is completed. And with that, I would like to thank all of the participants. I would like to thank our speakers for their very nice contributions, and also the people in the background facilitating this webinar. And I wish you a pleasant afternoon, and see you next time with CLMS webinars. Bye-bye.